Hi, welcome back to CS170. Just here to kick things off. We have the last week here. This is week 14. So you'll notice that it's supposed to cover chapters 12 for this week, but actually I covered 11 and 12 last week. So I just put 22 onto this week. Doesn't really matter. You're going to be covering all of these for your final exam. So I just thought it was better to do 11 and 12 last week and then 22 this week. So just a minor change in the ordering of the lectures. But this week is basically to cover that, review for the final. You have, note this point here, you have the quizzes opening up on May 3rd. So for those of you that missed any of the quizzes, it's an opportunity for you to catch up, get those quizzes in. May 3rd, pay attention to that. I believe you probably saw the announcement from Professor Trees about opening up the answers for exam 2. That's only open for a limited period of time. So whatever you need to review on that, please review that. And then we'll go from there. So let me see here. On my section, you'll see that I've already set up for this week, April 26th. I put the resources here, which essentially is chapter 12 from last week. But then you'll see last week we had resources, so that'll pick up on chapter 22. So I'll be covering chapter 22 this week. Hopefully it should be pretty quick. Like I said, I want to try to keep this week pretty light so that you can prepare for the finals, get your quizzes caught up. For some of you that might have your assignments, late assignments, whatever, get caught up on all of that. So get those in there, take advantage of the lab hours this week, get whatever you need done, try to work on it this week. The other thing that, I put out there, I think like even last week, I didn't really have extra credit, except I just asked people to submit any topics that they felt like they needed to brush up on or some review for the final exam. I'll extend that to this week. So let me know if there's any topics that you want to cover. I'll try to cut some videos on that and post that out. And also just any feedback on the course so we can incorporate that, either for the final exam or this last week or, for future classes. So do feel free to send me feedback for this week. So there won't be extra credit. This week, I will go through all of the extra credit submissions that people have made and then update your grades accordingly with the extra credit from myself. This is separate from the extra credit from what the TAs are offering. So make sure you, if you're going for extra credit, you follow up separately with your TAs. Most of them are kind of working some sort of attendance as their extra credit. So, putting your name on their sheet, their sign-up sheet or something like that. So that's something you can follow with your TAs. Okay. All right. So let's get going with this. So basically chapter 22 covers the limits of computation. See here, I think that's kind of big enough. Okay, so these are some of the key concepts, and similar to what I was talking about last week, these are the types of things where it's probably ideal for you to make sure you read through the textbook. The textbook covers, these are basic highlights for the chapter, right? Understanding the Turing test, evolution of various computer intelligence examples, and I'll go through some of that. What does the universality principle mean? And talk about the work and the way it ties to the speed of the program, and then the idea of NP complete problems. So these are all within your textbook, covers a decent amount of detail. So my suggestion is, both for last week's topics and this week's topics, make sure you read through the book, take notes, and notably on these highlights that I'm putting out here, and be prepared to answer them on the final exam, because that's really where the final exam questions are coming from, right? So That's my suggestion on this. This is kind of a bit, like I said last week, a bit unlike things where you're doing programming or whatever, where, you know, I might show you in lecture some examples of stuff or point you to things like W3 schools, and you can pull examples from there. This section, similar to some of the historical type of context, is really driven from the textbook material. So do make the time to follow up and read through that, take notes, and use that for the final exam. Okay. All right. So let's move forward. All right. So here's the idea about computer intelligence, right? And you know, one of the early things that came up in this area was this idea of the Turing test, right? This right here, Turing test. So basically, you have like a blind test, right? So this person here, C, is the tester. And then basically, there's going to have some sort of engagement, you know, conversation, asking questions, and basically not be able to tell the difference on the other side of this blind taste test, I guess you can call it, that, you know, the person is a person or a machine that's answering. Okay, so that's really the idea of the Turing test. And theoretically, when you get to that point, that's when the machine is quote unquote intelligent. Okay. So yeah, so this is important here. I'm not going to read this out to you, but basically talking about you know, basically having a conversation, right? Having a, instead of just kind of saying, well, let me see if you can crunch away at a math problem or something like that. See if you can have a conversation, right? And that there's a lot that gets into that type of thing, right? So number one, in this case, we're talking about English, right? So analyzing the language, I'll just say language, just more general instead of just saying English. But in this case, you're talking about English, you know, understanding like context, and being able to turn that into something of like of an answer. How can I provide an answer, assuming I understand what the question is, okay? So here's some couple examples that have been in the news in the past, talking about has the Turing test passed. So one is this one, you know, talking about like, you know, whether this AI passed the Turing test. You know, at the time, you know, I guess there was some buzz about that. But then, and I think maybe there's still some debate on it, but I think at the end of the day, they're kind of passing this off as not really passing the Turing test, right? Because they kind of, you know, put this like caveat there saying it's a 13-year-old Ukrainian boy. You know, so you know, I guess they kind of do that to kind of try to limit the scope, right? But the Turing test, in this case, I think, although there's still debate, I would just say probably not, right? So then you also have things like Google, right? Google has done their shot at this, and whether that passed the Turing test or not, still open for debate, but getting closer, right? There are things that it gets pretty close. I think, and some of you may or may not have tried this. I've actually been using Google. I have like a Google Pixel that has different things on there. Probably any of the Android phones. You can do things like screen your phone calls. So so Google will answer and do some screening your phone call. You can use Google to call up a restaurant and make reservations for you and stuff like that. So still very limited in scope, but it, you know, it's getting there. It seems to do certain things, and there's other different things that you might see play out in terms of like chatbots. Probably some of you have been like on you know, on the website, and then there's like a little chatbot that pops up and you can ask a question. Some of it is very clearly like no way it's a you know, anything other than a machine. But some of the chatbots are actually pretty decent. You can have like a sort of a decent conversation, but still the scope is not quite the same as what you call the passing the Turing test. Okay, so I think there's been a number, what I just mentioned here, these things. There's a number of things that have kind of moving along that way, but hasn't quite gotten there in terms of really passing the Turing test. Okay. Here's another one. This is back in the early days when things were kind of done on the mainframe and more like text-based screens and stuff like that. So there's this like computer program called ELIZA, and it was developed over at MIT, right? And then you would have this conversation back and forth with them, okay? And so you have a dialogue, and they would look for some keywords and then provide some responses. So it's sort of like a chain or a tree of different things where, oh, if you do this, then this is likely what the person's asking about or talking about, and then here's some different responses and stuff like that. So it's sort of maybe like a brute force way of doing things, and I'll kind of go more into that when we go into like computers playing chess and stuff like that. But this is an early attempt of having like a computer be able to carry out a conversation. So like I said, this is text-based. So you would see things like this, and you would have this conversation, as you can see on the screen. Okay. Okay, so this is a key point here, right? So like things like this, the computer doesn't really understand, right? It's just kind of looking for some key things and then, doing a response based on that, right? Here, that's pretty key, right? So the computer understanding the situation and then acting on that understanding, right? And later on, we're going to get into something like IBM Watson doing Jeopardy and how it goes through this step to understand the situation and then act on the understanding. Okay. So there's another key point that kind of builds on this, kind of saying, well, the actions can't be scripted or pre-programmed, right? So it's almost like, well, okay, if I come to talk to someone, here's all the different responses they could potentially say to me. And then based on seeing that, then I'm going to have these responses pre-programmed, right? And it'll just kind of work down the tree, like I was saying, which is essentially what ELIZA is doing. Okay, so this is another key point. Okay, and then, like I was mentioning before, they have to understand natural language processing. Okay, that kind of leads into you being able to understand the situation, right? And in this case, it's a little bit quote unquote biased towards English, right? Being that language. But yeah, that's kind of how this was thought through in the early days. Obviously, right now you can kind of say, yeah, well, could be English, it could be another language, whatever. But this idea of understanding natural language, okay? So playing chess. So playing chess, as it says here, it doesn't require natural language. You just need to understand all the rules, and then you go from there. So playing chess is a challenging game for those of you that may have played it. And, it's basically, I would say playing chess is sort of like a number crunching exercise, right? So that's more like to kind of look at the hardware or the algorithm capabilities of the computer, right? It doesn't have to necessarily be intelligent to be great at playing chess. Okay, so through the series of like improvements that people invested in to improve computers to ultimately beat grandmasters at chess, it wasn't necessarily an intelligence type of thing for computers. It was more of like a number crunching exercise, whether it's at the hardware level or at the algorithm level. Okay. So as it states here, I don't want to read through all of these different things, right? But like here, right? So computers understanding all of the legal chess moves and then being able to put together all of the different paths and then crunch through all the paths, right? That's one of the one of the things that chess playing does with computers. What I was alluding to in terms of being able to crunch through all of the permutations. Okay, so so you basically have the chess game, you're taking in all of the positions on the board, right? And then you have like a series of boards or configurations, right? I would call them permutations, but basically you have all of the different possible moves that can happen, right? And just because of like the way the game of chess is set up, i.e. different than checkers, right? So chess, has a lot of different moves, right, that it can do between all the pieces. So there's like a lot of combinations, right? And that's kind of why it stresses the early computers in terms of like their hardware or algorithm capabilities, right? So to be able to scale up and come back with a response in a reasonable period of time is the computational challenge for playing chess. Okay, so as it says here, one configuration or legal move, which is there's a whole bunch of pieces on the board at the beginning, produces another configuration, right? So one configuration to another configuration. And then there's a response, right? So there'll be the player on the other side that's going to produce a move, and it'll be a different configuration. So it kind of builds on each other. So this is where it comes into what they call a game tree, right? And there's different weightings on depending on which path or which node of the tree that you're going to go to, right? So obviously, if like the score is positive, that's a good move. If it's a negative, then it's a bad move, right? And so it's not just like the idea of looking at the next node to say whether that's a good move or a bad move, right? It's more like, playing out, at multiple levels. They're going down the depth of the tree. So multiple levels, because you have to kind of look ahead. So if I do this, what's my opponent potentially going to do, right? And all those different combinations, you kind of play all that out and then see what has the best score, okay? So that's what this is talking about. The higher the score, the better the move, okay? And then this is what another key point. So they have to look ahead, right? So it's not just the next move. It's really kind of like going deeper into the tree, right? To understand like, well, if I do this, these are the 6 different things that the opponent can do. And then I'm going to have these like other maybe 6 things off of each of those, right? You can see how quickly like the number of configurations exponentially grows. So it will play through all of those very quickly. And then it will have a weighting for each of those, right? And so, actually I misstated, I shouldn't say play through it. They've already kind of basically stored all of these different combinations in memory, right? And then you're just basically, exploring that. And so this is kind of demonstrated a little bit, right? So here's like what they call the game tree, right? So you can picture this top node here is your starting position, right? And then let's say, person A or player A does one move, right? And maybe it's this one. So then all of a sudden you kind of go down to here, and then there's another reaction, right, from the other player, and then it kind of goes down to one of these. So you can see how quickly it goes down to here. So what happens is that, all of these different combinations obviously is something that if you have a huge amount of memory, you would just be storing all these different combinations all the way from the top all the way down to like the lowest level, which is a lot of combinations, which back in the old days, that was a big challenge to get that much memory to be able to store all these boards, right? And then be able to evaluate, however many levels you want to evaluate. But as computing power improved, hardware improved, whatnot, then this became a lot easier over time. Okay, so everything I've just said is kind of stated right here. So it considers every possible move, evaluates them. This is look ahead. Okay, so it's looking ahead at all the different possibilities. Okay, so checking the whole game tree is generally impossible, but I would say at this point, given like the degree of computing power that we have, it's not that impossible. You can just really crunch through it at this point, given how much computing power that we have. But anyway, you can see like when I talk about exponential growth, like you can see this, right? If you go through like the first 6 moves, you get to a 500 million boards, okay? But coming back to here, right? So you can have a lot of boards here, right? But it's not like once I do one move, if I come to here, then I don't have to worry about all these other boards, right? Like all these other boards here. So it's once you come down to here, and then you come down to here. So in theory, yes, I go through like the 6 levels here and I count all of these. Well, that's a lot of boards, right? But when I tell you there's this many boards here, it's not like it really has to evaluate all of those. Once you've gone to a certain configuration, you've taken a certain path, you've actually eliminated all these other ones over here, right? So it's still a lot, but maybe not as much it's making it out to be here, right? So like I said, it's one of those things that you basically store this type of tree and then you're able to traverse this. Okay. So here's another important concept is the idea of parallel computing. Okay. So it's one of those things where instead of having to do things in a serial fashion where you only maybe using one CPU, one line of path for your computation. In some cases, you're required to do, you really need to do that because things are dependent on each other. So you kind of have like one computation leads to another computation leads to another computation. But it doesn't necessarily have to be that way. And so in some cases, sort of like with let's say looking ahead, right? If you want to try to look ahead to all these different types of paths, you can line them up. Then you can do parallel computation. Okay. So this is the key point on this slide here. So parallel computation, you can say you're applying several computers or several CPUs to do the processing. So this crunching through these game trees is made faster by doing things in parallel. Okay. So this is basically just talking about this grandmaster Garry Kasparov, who was pretty much like the key guy during all this time where they were developing the chess playing computer. Okay. And so basically they talked about the hardware for the computer that was initially used for this computer they call Deep Blue. Okay. And it's basically 32 general purpose and then 256 basically customized chess CPUs. Okay. So basically they talk about like where it was at that point where the computer initially took a game against Kasparov, but then the following year, not only did they improve the algorithms, but I think the hardware side of things significantly improved. And then they were able to beat Kasparov the following year. Okay. Um, Okay, and so this is what I kind of was alluding to, where basically this was a problem not really in terms of computer intelligence per se, but it was more by hardware, so and algorithms, right? So you just basically were able to crunch through those game trees. Okay, so Deep Blue was able to look deeper, right? So I think that's a key point here. Um, And then this is the point, it's completely specialized to chess. Okay, so not that it wasn't a good thing, it was a good achievement. You were able to demonstrate certain capabilities of the computer, but not quite there in terms of what you're trying to get to with computer intelligence. So the next bit is AlphaGo. Okay, so this is from Google. This is actually more recently. So talking about the complexity for this, this is a bit more complex than playing chess. And so this is where they use basically learning with neural networks. So it's machine learning. So when you to contrast this from the chess standpoint, on chess, basically people program all these different boards and how to analyze those boards and traverse those boards. That was basically all people putting those things in there. So it's almost like me, passing in all of these math algorithms or whatever, and then the computer is able to execute along those lines. So but the difference here with AlphaGo is basically it didn't tell it anything. Basically, just told it to go play many games, right? I mean, it's a computer, right? So the computer can just play a whole bunch of games, and then it basically built out these trees itself, right? It basically built out everything. It taught itself, what were the best moves to win the game. Okay. So all of these different things here were built up by the computer, in this case for AlphaGo, right? Again, because of like the basically the scale, right? It's much bigger scale than chess. So this is a case where it works out well, where the computer can play the game over and over again against another version of itself, and basically play out all the different possibilities, and then pick up the optimal path through these, right? So that's what they have here with these weightings here. So all of these are different points here, and then you make the next move, you make the next move, and you make the next move. And then you have all these different weightings here. And then you try to pick out which one is the optimal path, okay? Okay, so the next one, we go into Watson. I think I've been recording for a bit, so I'm going to take a pause here, and then I'll come back with another lecture to start with Watson. Okay, so I'll come back shortly.